double-slit. A single photon acts like a wave when no one watches and like a particle when you look. You sit there thinking light is either a wave or a particle. Then the lab shows you both at once. That is the glitch. In the classic setup, a beam of light passes through two narrow gaps and lands on a screen. When nobody records which gap the photon took, a pattern of bright and dark bands appears. The pattern is what waves make when they overlap. But when detectors watch, which gap the photon goes through, the bands vanish. Instead, you get two clumps, each one where a particle would land. The act of looking changes the outcome. Modern labs send single photons one at a time. Each photon lands as a single dot. Slowly, the dots pile up into that same wave pattern. The implication is brutal and simple. When you refuse to measure, the photon behaves like a smeared possibility that interferes with itself. When you force a definite answer, the possibility snaps into a single result. Physicists explain this with quantum superposition and wave function collapse. Decoherence gives a practical account. But for you, the takeaway is immediate. Reality here does not march forward with fixed facts. It holds many possibilities until an interaction forces one to happen. That feels like a software process choosing a frame to render. Some interpretations say nothing mystical is happening. Others say the universe is stranger than your gut expects. Either way, you now have a concrete example where observation alters what the world does. It is one of the clearest laboratory demonstrations that what we call reality can behave like a system that glitches when probed. But this is only the start. There are experiments that go further, even ones that make it look like the future is rewriting the past. You can test this in the lab, and people have. Scientists fire single electrons or photons through the slits. Each hit shows up as a single dot. One dot, then another, 100 dots. Slowly, the wave pattern appears. That pattern was hiding inside each particle when you were not forcing it to choose. Physicists call this superposition. It simply means the particle carries many possible routes at once. The math describes all those possibilities as a wave. When you measure, the wave gives a single answer. The measurement is not a passive glance. It is an interaction that asks the system to pick one path. Why does this feel like a glitch? Because in normal life, an object does not wait for you to decide how it exists. A ball is either here or there, whether you look or not. In quantum land, the outcome can depend on whether you set up a detector. That flips the usual script. The world behaves like a system with hidden rendering rules that reveal themselves only when probed. There are ways to probe without forcing a full collapse. Physicists call them weak measurements. Those methods let you peek at the quantum behavior without collapsing it completely. They give partial information and a glimpse of the in-between. The results are subtle but real. They show traces of that overlapping behavior, even when you are trying not to force a final answer. Beyond the physics, there is a practical thread. The same ideas underlie quantum computing and quantum sensing. If you can control superposition and measurement, you can build devices that do things impossible in a classical world. That is why these quirky experiments are more than party tricks. They point to new technologies and new ways of thinking about cause and effect. So, the double slit is not a trick. It is an invitation. The invitation is to accept that at a fundamental level, reality can wait until you ask and then answer in a way that looks, for all practical purposes, like a glitch. Quantum entanglement experiments. You take two tiny particles and link them so tightly that measuring one immediately tells you something about the other, even if the other is far away. In the lab, researchers create entangled photon pairs and send them to separate detectors miles apart. Measure the polarization of one photon, and the other photon shows a matching or opposite result instantly. That is not a coincidence. That is a correlation that cannot be explained by ordinary signals traveling between them. In 1964, John Bell found a way to test whether those correlations could come from hidden instructions carried by the particles. He wrote inequalities that local hidden variable models must satisfy. If experiments violate Bell's inequalities, then local realism is impossible. Alain Aspect and his team ran those tests in 1982 using fast switching devices, so the measurement choices could not influence the other photon in time. They found clear violations. Later experiments removed remaining loopholes. The result is robust. Nature does not behave like two separate boxes that hide fixed answers inside them. What does this mean for you? It means that far apart pieces of the world can act like a single connected system. It means reality is not fully local in the way you learned as a child. It feels like a glitch because the universe ignores ordinary distance when it comes to information about entangled properties. Scientists disagree on the interpretation. Some accept non-locality and abandon local realism. Others keep realism and allow non-local influences. There are interpretations that avoid spooky action by changing what we call reality itself. Beyond philosophy, entanglement is practical. It powers quantum cryptography and quantum teleportation experiments. The same strange link that bothered Einstein now underpins secure communication and future quantum networks. A lab at dawn. A graduate student tightens a connector and watches a counter that clicks when a photon arrives. For years, the problem was not making entangled pairs. It was proving those links were not tricks. So teams designed ever stricter tests. They sealed detectors in isolated boxes. They used random number generators to set measurement angles at the last possible moment. They timed everything so no ordinary signal could carry an answer. Each time, the universe refused to behave like separate parts. Then came the loophole-free era. In experiments with electron spins and remote photon stations, researchers closed the detection loophole and the locality loophole at the same time. The statistics screamed violation of Bell's inequalities. That is not an accident. That is nature telling us the correlations are real and unavoidable. Engineers took the same physics and turned it into tools. Quantum key distribution uses entanglement to make codes that reveal eavesdroppers instantly. Quantum teleportation transfers the state of a particle to another without moving matter in between. Those sound like science fiction. They are lab tools and prototypes now. The spooky link that unsettled Einstein is the backbone of secure networks and future quantum internet ideas. Philosophers and physicists still argue about what it means. Is the world non-local, or is locality a misleading concept? Do we need new physics or a new way of talking about information? Those debates matter because the experiments are clean and repeatable. The strange connection is no longer a rumor. It is a working piece of reality that breaks everyday expectations. What if our most trusted idea of separateness is only an approximation? Delayed choice quantum eraser. You send a single photon through a double slit. It lands on a screen as a single dot. Later, you decide whether to learn which slit it went through. That decision can come after the photon hit the screen. That is the core shock. In the lab, researchers split photons into entangled partners. One partner, called the signal, goes to the screen. The other partner, called the idler, travels to a set of detectors that can either preserve which path information or erase it. The trick is that the choice for the idler is made after the signal already registered. When which path information is kept, there is no interference. When that information is erased, the interference pattern reappears in the correlated data. The past outcome looks different depending on a later choice. The experiment by Kim, Yu, Kulik, Shi, and Scully in 1999 made this concrete. They used precise timing and entanglement to force the delayed choice. The results do not let you send messages back in time, but they do show that which facts become real depends on the entire measurement setup, even choices made later. Most physicists explain this inside standard quantum theory. They say the correlations reflect information and context, not causal rewriting. Others offer stranger words like retrocausality or relational reality. Philosophers keep arguing. Technologists stay quiet and use the math. If future choices can affect what we call the past, then what does that make a single recorded fact? A researcher in a dark room adjusts a fiber optic cable. Light clicks through, and detectors register arrivals. Years after the first delayed choice experiment, teams pushed the setup further. They separated the entangled partners by greater distances. They ensured the choice to preserve or erase information was made in a region that could not influence the other by any ordinary cause. The same pattern held. The correlations persisted. Crucially, you cannot use this to send a message into the past. The experiment does not let you change an outcome you already read on a screen in a way that carries information to someone else. The oddity shows up only when you compare correlated records. It is about what can be known together, not about a secret time machine. Physicists split into camps. Some say the math is enough. They argue that quantum mechanics describes probabilities and correlations, and that questions about retrocausality are semantic. Others propose deeper explanations. A few take seriously the idea that events are not fixed until the full measurement context is set. The debate is active and healthy. There is a practical side, too. These experiments forced clearer thinking about information. They sharpened tools for quantum communications and for studying decoherence. They also make you look at everyday records differently. When you trust a video or a sensor reading, you assume it reflects an unchangeable past. These experiments remind you that at the quantum level, recorded facts are sometimes contingent on later choices. If the past can be conditioned by future measurement, then which parts of history are truly settled? Quantum Zeno effect. You check again and again and nothing changes. In quantum labs, that is not a joke. It is a real effect, where frequent measurement can freeze a system in place. The idea was put on paper in 1977 by Misra and Sudarshan as a quantum version of Zeno's ancient paradox. The formal claim seemed wild. If you measure an unstable state often enough, it will not decay. In 1990, Itano and colleagues trapped a single beryllium ion and hit it with rapid laser pulses that acted like measurements. The ion refused to flip to the other state at the expected rate. The more often they probed it, the longer it stayed the same. Here is the simple intuition. A quantum state evolves as a spread of possibilities. Each measurement forces a partial reset. Do that quickly enough, and the system has no time to move away, so it keeps returning to its starting point. It is like pressing rewind faster than a scene can change. Physicists explain the effect with wave function projection and decoherence control. Experimentalists use it to protect quantum states. But there is a twist. Under different conditions, frequent probing can speed up decay. That is called the anti-Zeno effect, and it shows the outcome depends on how you measure. The result is practical and philosophical. Practically, it helps preserve fragile qubits in quantum computers. Philosophically, it forces a hard question. If observation can halt natural evolution, what does that say about the flow of time and the role of the observer in reality? It freezes change. It asks whether change is a property of the world or a property of the way we look at it. You walk into a cryogenic lab. A vacuum chamber hums. A lattice of light holds a cloud of atoms so cold they barely move. Researchers fire pulses of light like taps and watch what happens. With the right pulse rhythm, the atoms will not tunnel out of their trap. They stay frozen in a state they would otherwise leave. The act of checking arrests the natural flow. Mark Raisin and other teams showed this with cold atoms. They made tunneling slow or stop by varying how often they probed the system. Then they found the flip side. Under other probing conditions, frequent measurement makes change faster. That is the anti-Zeno effect. The two together teach a sharp lesson. Measurement does not simply reveal. It can speed up or slow down what unfolds, depending on how it is done. Engineers saw an obvious use. If observation can protect a fragile quantum state, then it can help build better qubits. Quantum error suppression techniques borrow the same logic. The very thing that once sounded like a philosophical puzzle now helps keep quantum information alive long enough to do useful work. Some physicists treat this as control engineering. They focus on protocols and noise. Others insist it raises deep questions about agency and time. When observing becomes a technique to shape evolution, we must ask who or what gets to shape reality. If measurement can be a brake or an accelerator on nature, then what does that make observation itself? Macroscopic quantum tunneling. You stand beside a fridge that is colder than outer space, and you touch a tiny superconducting loop with a probe so precise it barely disturbs anything. In the middle of that loop sits a junction where a collective quantum phase can behave like a particle on a hill. Classical intuition says the phase should be trapped. In the quantum world, it sometimes simply appears on the other side. The picture physicists use is a washboard potential where the phase sits in a valley. Normally, it climbs out only if it has enough energy. At ultra-low temperatures, thermal nudges vanish. But quantum mechanics allows tunneling through the barrier. In the mid-1980s, experimental teams cooled Josephson junction circuits to millikelvin temperatures and measured escape rates that could not be explained by classical heating. The observed escapes matched quantum tunneling predictions. Theorists had warned this was possible. Leggett and others had argued that macroscopic variables could behave quantum mechanically. Experimentalists like Martinez-Deveray and Clark translated that into devices and data. The result blurred the line between microscopic and macroscopic. Something that looks like a classical circuit can do what a single electron does in a tunnel junction. Practical stakes are high. The same physics underlies superconducting qubits. Tunneling events can be errors or the very mechanism for state control. Engineers exploit and fight it at the same time. Philosophers ask whether macroscopic realism survives. If a circuit with billions of electrons can tunnel as a single quantum object, then where exactly does the classical world begin and the quantum world end? If machines built from everyday materials can behave like quantum particles, then how firm is the ground under our ordinary sense of reality? A technician holds a tiny circuit under a microscope and watches a histogram slowly fill. Those switching currents are the fingerprints of tunneling events. They are rare and noisy. To see them, you must eliminate heat and electromagnetic noise, and then wait. That patience paid off. The distributions did not match thermal escape. They matched quantum predictions. The experiments taught engineers something practical and unexpected. Tunneling can produce sharp jumps that ruin a qubit. At the same time, it can be harnessed for readout and control. Designers now balance materials choices, circuit geometry, and coupling to the environment to manage tunneling rates. The very effect that once proved the quantum nature of macroscopic variables is now a design variable in quantum processors. Companies building superconducting quantum chips fight these quantum leaks while using related effects to perform high-fidelity measurements. That practical application changes the tone of the whole conversation. These are not just thought experiments. They are the physics behind prototypes that perform calculations and tests no classical device can do efficiently. On the philosophical side, this pushes questions into public life. If engineered devices made of everyday materials can exist as coherent quantum objects, then the separation between the quantum and the classical is engineering dependent. Some scientists say the boundary is pragmatic. Others think it points to new physics waiting at larger scales. The laboratory work is precise. The debate is wide. The machines are real. The question remains sharp and simple. Where does the quantum end and the ordinary world begin? Simulation hypothesis tests. Cosmic rays slam into our atmosphere with energy so high they light up detectors like tiny fireworks. Some physicists asked a blunt question. If the universe were a computation with a finite grid, what patterns would show up in those showers? 2012 saw a careful paper by Silas Bean and colleagues that turned the idea into a real test. They argued that a lattice simulation would impose direction-dependent limits at the highest energies. In plain terms, spacetime would have a resolution. At extreme energies, particles would reveal that grid with subtle anisotropies or cutoffs. Observatories, such as the Pierre Auger Observatory and the Telescope Array, measure ultra-high energy cosmic rays. They map thousands of events. Scientists look for unexpected direction preferences or energy ceilings that cannot be explained by astrophysics alone. So far, the evidence is ambiguous. No smoking gun has been found. That does not kill the idea. It only narrows which kinds of simulation could fit our data. Mainstream physicists remain cautious. Lorentz symmetry and other deep principles make simple lattice simulations unlikely. Others are excited because this is how philosophy becomes science. The simulation hypothesis goes from thought experiment to falsifiable claim. There are deeper implications. If spacetime had a pixelation scale, then the notion of continuous space would be approximate. If a simulator set limits, then we might find fingerprints in places we already study. The hunt pushes instruments and theory in new directions, and it makes the metaphysical question surprisingly practical. If the sky contains a hint that reality is computed, will we recognize it when it appears? Night at the control center. Screens trace particle showers. Analysts argue over small deviations that might be statistical flukes. That argument is the heart of the simulation test. Bean and his colleagues gave scientists a clear target, a plausible signature. Teams hunted that signature. They scanned maps. They checked directions. They compared energy spectra. So far, there is no clear fingerprint. That means simple lattice simulations are unlikely. It does not mean the idea is dead. A clever simulator could hide Lorentz symmetry or use non-lattice methods that leave no obvious imprint. The absence of a simple pattern forces better thinking. It pushes scientists to design subtler probes. Researchers now test for tiny energy-dependent speed differences in gamma-ray bursts. They probe whether high-energy photons arrive fractionally earlier or later than low-energy ones. They study the polarization of light from distant galaxies. They look for irregularities in the cosmic microwave background. Each null result tightens the constraints and narrows the space of plausible simulations. The scientific posture is careful. The simulation hypothesis moved from philosophy into the lab. That is remarkable. It shows how metaphysical proposals can be subjected to real data. At the same time, the exercise highlights a limit. To detect a simulator, we must make assumptions about what a simulator would do. If those assumptions are wrong, we will see nothing. Science can rule out classes of simulations. It can never prove the negative in absolute. The sky keeps giving us data. We refine our questions, we sharpen our instruments, and we keep listening for a pattern that looks more like design than chance. If reality were coded, what signature would make you convinced? Schrödinger's cat. Picture a sealed box, a cat, a vial of poison, and a radioactive atom that may or may not decay. The thought experiment from 1935 was not cruelty, it was a challenge. Erwin Schrödinger wanted to show that applying quantum rules to everyday objects leads to absurd conclusions. If the atom is in a superposition, then so is the cat, alive and dead at the same time until you open the box. For decades, that was a classroom paradox. Then, experimentalists began to make superpositions larger and larger. Superconducting qubits and trapped ions have produced states that are, in a technical sense, macroscopic. Teams at universities showed interference in circuits containing millions of electrons. Other labs placed molecules and mechanical oscillators into fragile superpositions. These are not thought experiments, they are data. Why do we not see cats that are both alive and dead on our kitchen table? The mainstream answer is decoherence. A quantum superposition is extremely fragile. Interaction with the environment picks out a definite outcome almost instantly. Decoherence explains why macroscopic superpositions decay so fast and why classical reality appears stable. Not everyone is satisfied. Some interpret decoherence as an explanation of appearance only. Others propose objective collapse mechanisms that change quantum theory at large scales. Many worlds enthusiasts say the cat lives in multiple branches of reality. Each view survives because the experiments are subtle and the interpretations are bold. So, the laboratory has moved Schrödinger's cat from parable to experiment. The question now is practical and urgent. At what scale do quantum possibilities stop being just possibilities and become a single fact? You close the box in your mind, and the thought experiment fades into a laboratory bench. Engineers build devices that behave like the cat in miniature. In 2010, and the years that followed, teams created superposition states in circuits and in tiny drums that vibrate like violin strings. They put whole mechanical pieces into delicate quantum states and watched interference appear and vanish. Decoherence explains much of what we see. Every interaction with air or stray light or thermal motion scrambles the fragile phase relationships that make superposition visible. That rapid loss of coherence is why cats do not sit both alive and dead on kitchen tables. In practice, decoherence converts quantum possibilities into apparent classical facts almost instantly. Still, the interpretations do not agree on what that really means. Many worlds says every outcome exists in branches we cannot access. Objective collapse models say the wave function really does break when systems reach a certain scale. Relational views say properties become definite only in relation to observers or other systems. Experimentalists keep testing, because each experiment shifts what interpretations remain plausible. There is a practical thread that ties all this to your life. If a superconducting circuit can be a coherent quantum object, then the same rules that govern the cat experiments govern tomorrow's quantum computers. Controlling decoherence is not just philosophical, it is engineering. The deeper question is stubborn. When a measurement makes a fact real, are we discovering something or are we helping to create it? Which answer will change the world first? Wheeler's delayed choice experiment. You set up an interferometer with two possible paths for a photon. At the end, you can choose to measure which path it took, or let the paths merge and watch for interference. The twist is brutal. You make that choice after the photon has already entered the apparatus. John Archibald Wheeler proposed this in 1978 as a thought experiment. He wanted to push the weirdness of quantum mechanics to its limit. If you can decide how to measure after the photon is already traveling, then it seems like your present choice determines the photon's past behavior. Did it take one path or both? The answer depends on what you decide to look for. In 1984, Jacques and colleagues at the University of Maryland ran the first real test. They used a beam splitter and fast switches to change the detection setup while the photon was in flight. The results matched Wheeler's prediction. When they chose to measure which path the photon behaved like a particle on a single route. When they chose to look for interference, the photon behaved like a wave that took both paths. The choice made after entry determined what the photon seemed to have done before. Later, experiments tightened the setup. Teams used longer paths and faster switches to ensure the decision happened well after the photon committed. Some used astronomical distances, letting photons from distant quasars travel billions of years before experimenters on Earth decided how to measure them. The correlations held every time. Physicists explain this without true time travel. They say the photon exists in a superposition of possibilities until measurement collapses it. The past is not rewritten. Instead, what we call the past depends on the full context of observation. That context includes future choices. Others find that explanation uncomfortable. A few propose retrocausal models where future measurements genuinely influence past states. Most mainstream scientists reject that view, but the debate continues. For engineers, the lesson is practical. Quantum systems do not have fixed properties until you measure them. The measurement setup matters as much as the system itself. That insight drives quantum information research and informs how we design detectors and communication protocols. Philosophically, the experiment is a hammer. It forces you to ask what a fact is. If a photon's history depends on a choice you have not made yet, then facts are not static records. They are outcomes shaped by the entire measurement process. A technician adjusts mirrors in a dark lab. Photons stream through, and choices flip in microseconds. The data accumulates, and the pattern is always the same. The measurement made after the photon traveled determines what it looks like the photon did. Modern versions use quantum random number generators to ensure the choice is truly delayed and unpredictable. They separate the decision point from the photon's path by vast distances or long delays. Every refinement confirms the result. Some experiments sent photons through fiber optics across cities. Others used light from distant astronomical objects where the travel time is cosmic. In each case, the measurement choice comes after the light has been traveling for years or microseconds. The photon still behaves according to that choice. The implication cuts deep. In classical thinking, an event happens and then you learn about it. The event is independent of your method of learning. In quantum experiments, the method of learning is part of what defines the event. You cannot separate the system from the measurement context. Researchers now use this insight to refine quantum technologies. Delayed choice setups inform how we think about quantum communication and sensing. They show that information is not a passive record, but an active part of how reality unfolds. Critics say the explanation is simple if you accept superposition and delayed collapse. Enthusiasts say it reveals something profound about time and causality. Either way, the lab results are clear and repeatable. If the method you choose in the future affects what you say happened in the past, then where is the line between observer and observed? Discrete time tests. You glance at a clock and time feels smooth. Physics asks a stranger question. What if that smooth flow is only an appearance? Some quantum gravity ideas suggest time might be discrete. Instead of a continuous river, you could have tiny ticks, like frames in a film. Physicists call the natural unit the Planck time. It is about 5.49 times 10 to the minus 44 seconds. At that scale, classical ideas break down. One approach, called causal set theory, developed by Raphael Sorkin and others, replaces spacetime with a discrete set of events linked by cause. If time is quantized, there could be small anomalies we can measure. How do you test something so tiny? Astronomers look for energy-dependent delays in gamma-ray bursts. If very high energy photons slow differently, you might see a spread in arrival times for a distant burst. Precision atomic clocks and matter interferometers probe time at a different scale. Cold atom experiments and optical clocks can test whether time ticks differently under extreme conditions. So far, there is no decisive signal. Observatories and laboratory teams place ever tighter bounds. That does not mean the idea is wrong. It only means that if space-time has a grain, it is very fine, or cleverly hidden. Still, the search is vital because it changes how we think about causality, and about what it means for an event to happen before or after. If time itself can jitter at the smallest scales, what does it do to cause and effect, to memory, to the way experiments record history? A researcher in a lab compares two atomic clocks that disagree by less than a billionth of a second over a year. That precision makes testing time itself possible. Scientists use optical clocks, atom interferometers, and astrophysical observations to look for the tiniest departures from smooth time. One route is to study high-energy photons from distant gamma-ray bursts. If spacetime is granular, then photons of different energies might arrive a hair apart after traveling billions of light-years. Telescopes and timing arrays search for systematic spreads. So far, the data limit many classes of models. No clear energy-dependent delay has been confirmed. Another route uses atom interferometry. Cold atoms are placed in superposition and allowed to fall or drift. Tiny differences in phase accumulate if time behaves oddly at small scales. Laboratory teams measure those phases with exquisite care. Again, the results place tight bounds. There are also Lorentz invariance tests that check whether the laws of physics look the same in all directions and speeds. Violations would be a smoking gun for discrete spacetime. Precision experiments and cosmic observations constrain such violations to extremely small levels. What do these null results mean? They are not failure, they are guidance. Each limit excludes naive models and points theorists towards subtler possibilities. If spacetime hides its discreteness, it does so cleverly. The search is ongoing and creative. It blends the very large with the very small and demands technologies that would have been unimaginable a generation ago. If time can hide its texture, will we need new physics or new instruments to see it? Placebo effect. You go to a clinic with pain and expect relief. A clinician gives you a pill that contains no active medicine, and you feel better. That is not magic. It is a measurable biological response that researchers have tested for decades. In 1955, Henry Beecher published a paper called The Powerful Placebo. He reviewed clinical trials and argued that many improvements came from expectation and context. Later critics refined his methods, but his main point stuck. Belief influences outcomes. Modern neuroscience made it concrete. Brain scans show that placebo analgesia activates the body's own opioid pathways. Researchers using PT imaging found that expecting relief releases natural opioids in the brain. Other studies show changes in dopamine and in immune markers. Open-label placebos, where patients know they are taking a placebo, still produce benefits in some conditions. That complicates the ethics and changes how doctors might use expectation ethically. There is a darker side called the nocebo effect. Negative expectation can produce harm and side effects. Telling a patient about possible side effects can increase their chance of experiencing them. That reality forces doctors to balance informed consent with the risk of harm from suggestion. Scientists debate magnitude and mechanism. Anthropologists show placebo responses vary across cultures and rituals. Clinicians weigh whether using placebos can ever be honest and beneficial. Philosophers ask if mind-influencing body undermines a strict materialist view of reality. If expectation can change measurable physiology, then which parts of what you call real depend on minds that believe in them? A scientist lies in an MRI scanner and watches images of their own brain light up when a placebo is given. Researchers see patterns that match pain relief. They also measure biochemical changes. In some studies, placebo analgesia triggers natural opioid release. Other studies show dopamine shifts in conditions like Parkinson's. Immune markers change in response to expectation and conditioning. Clinical trials now test open-label placebos, where patients know they are taking inert pills. Surprisingly, some patients still improve. That outcome forces a rethink. It suggests that part of the placebo effect is not deception, but ritual and the meaning of treatment. Cultural studies back this up. Different societies show different placebo strengths. Ritual, context, and trust matter. There is also the nocebo. Telling patients about possible side effects can make them more likely to experience those side effects. The effect is real and measurable. That places a heavy ethical burden on doctors who must inform without causing harm. Psychoneuroimmunology ties these findings together. The brain, the nervous system, and the immune system communicate. Expectation modulates hormones, neurotransmitters, and immune responses. That is why belief can speed recovery or amplify symptoms. Scientists warn against magical thinking. Placebo effects do not replace genuine treatments. They can complement therapy and improve outcomes when used ethically. Doctors and ethicists debate how to harness expectation without deception. If belief can alter measurable biology, then what responsibility do we have for our own expectations and for the signals we send to others?